Good day, everyone. Welcome to another video episode for Senior High School STEM. The aim of this tutorial is to help grade 12 students in understanding the topics in general chemistry. So get ready to learn. Take a deep breath, have an open mind, and think that chemistry is easy and fun.
Our video lesson for today is General Chemistry 2 Self-Learning Package Quarter 1 Week 6 Thermochemistry, the First Law of Thermodynamics. Published in the Philippines by the Department of Education Schools Division of Iloilo, Luna Street, La Paz, Iloilo City. The law of conservation of energy, or first law of thermodynamics, states that energy can neither be created nor destroyed. It can only be transformed from one form to another, meaning the energy of the universe is constant. Exothermic change. A change when energy is released to the surroundings. Example, burning of fuels. Endothermic change, a change that involves absorption of energy from the surroundings. Example, photosynthesis. The energy absorbed or released as heat in a chemical or physical change is measured in a calorimeter. Temperature is a measure of the average kinetic energy of the particles in a sample of matter. The greater the kinetic energy of the particles in a sample, the higher the temperature and the hotter it feels. The Celsius and Kelvin are the unit used for temperature. The amount of energy transferred as heat is usually measured in joules. A joule is the SI unit of heat as well as all other forms of energy. The joule, abbreviated as capital letter J, is derived from the units of force and length. The joule is a rather small unit compared with other units for heat, the kilojoules, or kJ is also commonly used as a unit for heat. The total amount of heat obtained, which is actually the energy change when the reaction occurs, is called the heat of reaction. A concept related to heat of reaction is enthalpy change. Capital letter H refers to the heat transferred by a process that occurs at constant pressure. Specific heat is the amount of energy required to raise the temperature of 1 gram of substance by 1 Celsius degree or 1 Kelvin, because the sizes of the degree divisions on both scales are equal. Values of specific heat can be given in units of joules per gram per Celsius degree, joules per gram per Kelvin, or calories per gram per Celsius degree. Specific heat is usually measured under constant pressure conditions, so its symbol is C sub P, contains a subscripted P as a reminder. Sample problem. A 4.0 gram sample of glass was heated from 274 to 314 Kelvin, a temperature increase of 40 Kelvin, and was found to have absorbed 32 joules of energy as heat. What is the specific heat of this type of glass? And how much energy will the same glass sample gain when it is heated from 314 to 344 Kelvin? Again, we have to write the given, the unknown or the required, the formula, and the solution. Given is the 4 grams of sample, and the change in temperature is equal to 40 Kelvin, and Q, or heat, is equal to 30 joules. Unknown, Cp in joules per gram times Kelvin, and Q in joules. So, the formula. Cp is the specific heat at constant pressure. Q is the heat, M is the mass, and delta T is the change in temperature. We have those values, and what we need now is substitute the given data to the formula. So Q is 32 joules divided by the mass, which is 4.0 grams times 40 Kelvin. So dividing this is equal to 0.20 joules per gram times Kelvin. Joules per gram times Kelvin. Next, heat is equal to the specific heat at constant pressure times mass times the delta T. How did we have that formula? That is, we derive it by cross multiplying. Okay, so Q is equal to Cp times M times delta T. So Cp is equal to 0.20 joules gram times Kelvin times the mass, which is 4.0 grams, times the delta T, which is equal to 30. So grams and grams cancelled, Kelvin and Kelvin cancelled, and the answer is 24 joules. Let's go now to heat of reaction. The heat of reaction is the quantity of energy released or absorbed as heat during a chemical reaction. Consider the chemical equation below. 2 moles of hydrogen gas plus 1 mole of oxygen gas will form 2 moles of water in gaseous form. Water in gaseous form is vapor. The equation does not tell you that energy is evolved as heat during the reaction. Experiments have shown that 483.6 kilojoules of energy are evolved or released when 2 moles of gaseous water was formed at 298.15 Kelvin from its elements. Modifying the chemical equation to show the amount of heat produced during the reaction gives the following expression. So from this equation, we can now add 483.6 kilojoules of energy evolved or released. When it is evolved or released, that means the energy should be placed in the reactant side. So we can rewrite it as this one, okay, plus 483.6 kilojoules of energy evolved or released, okay, or it can also be rewritten like this. That means that the energy evolved or released is not included in the formula, but you can write it as delta H is equal to 483.6 kilojoules, but it is negative because it is evolved or released. A thermochemical equation is an equation that includes the quantity of energy released or absorbed as heat during reaction. The situation is reversed in an endothermic reaction because products have a higher energy than reactants. Energy now appears on the reactant side of a thermochemical equation that follows, indicating that it was absorbed during the reaction. When it is absorbed during the reaction, it is added in the reactant side. Or it can be also expressed as this, which is not included in the reaction, but you have to write delta H is equal to positive because it is absorbed. The energy absorbed or released as heat during a chemical reaction at constant pressure is represented by delta H. The H is the symbol for a quantity called enthalpy. The Greek letter delta, a capital delta, stands for change in. Therefore, delta H is read as change in enthalpy. An enthalpy change is the amount of energy absorbed or lost by a system as heat during a process at constant pressure. The enthalpy change is always the difference between the enthalpies of the products and the reactants. The following expression expresses an enthalpy change mathematically. Change in enthalpy is equal to enthalpy of the products minus enthalpy of the reactants, or is equal to the energy of the products minus the energy of the reactants. Thermochemical equations are usually written by designating the value of delta H rather than writing the energy as a reactant or product. By convention, for an exothermic reaction, delta H is always given a minus sign because the system loses energy. So here it is negative. When it is negative, that means it is an exothermic reaction and the system loses energy during the reaction. By looking at this graph, this figure, so here, this is energy, and here is the course of reaction. This is the x-axis, and this is the y-axis. So the energy of the reactants is higher compared to the energy of the products, which is here. So during the reaction, that means the energy was released, resulting to the lesser energy of the products. So the delta H is negative. For an endothermic reaction, delta H is always given a positive value because the system gains energy. It's here, positive. Looking at this figure, energy, y-axis, and the course of a reaction, x-axis. At the start, the energy of the reactants is low. During the reaction, it increases, and it ended that the products have higher energy compared to the reactants. That is why the delta H is positive. Energy is absorbed in this reaction, meaning that the initial energy of the reactants is lower than the final energy of the products. In this case, delta H is designated as positive. So we have a table to summarize. Sign of delta H, if it is negative, the type of reaction is exothermic. That means heat is released. When the delta H is positive, the type of reaction is endothermic and the heat is absorbed by the system. Keep in mind the following concepts when using thermochemical equations. The coefficients in a balanced thermochemical equation represents the number of moles of reactants and products and never the number of molecules. This allows us to write these coefficients as fractions rather than whole numbers when necessary. The physical state of the product or reactant involved in a reaction is an important factor and therefore must be included in the thermochemical equation. Physical states such as gas, solid, liquid. The change in energy represented by a thermochemical equation is directly proportional to the number of moles of substances undergoing a change. For example, if 2 moles of water are decomposed, twice as much energy, 4.83.6 kilojoules, is needed than for the decomposition of 1 mole of water. So, to decompose 2 moles of water, we multiply 483.6 times 2, which is equal to 967.2 kilojoules. Sample problem number 1. Calculate the heat of reaction for the combustion of nitrogen monoxide gas NO to form nitrogen dioxide gas NO2 as given in the following thermochemical equation. So this is our equation and we have the given. This is the equation that we need to look for, the required equation. So we have the given 1/2 mole of nitrogen gas plus 1/2 mole of oxygen gas forms 1 mole of nitrogen oxide gas, which has a standard heat of formation of positive 90.29 kilojoules per mole. The second equation is 1/2 mole of nitrogen gas plus 1 mole of oxygen gas forms 1 mole of nitrogen dioxide gas with the standard heat of formation of positive 33.2 kilojoules per mole. Then we have the unknown. This is standard enthalpy of reaction, delta H0 for the equation, for this equation. So the solution. Reversing the first reaction for the formation of NO from its elements and the sign of delta H yields the following thermochemical equation. So the first equation was reversed. When the equation is reversed, that means the sign is also reversed. So we have now NO gas in the reactant side and 1/2 mole of nitrogen gas plus 1/2 mole of oxygen gas in the product side. The other equation should have nitrogen dioxide as a product, so we can retain the second equation for the formation of nitrogen dioxide from its elements as it stands. So we have 1/2 mole of nitrogen gas plus 1 mole of oxygen gas forms 1 mole of nitrogen dioxide gas. Okay, and then we have the standard heat of formation is still positive because it was not reversed. Now, let's go back here. Why do we need to reverse the first equation? And why is it that the second equation has stayed as is? So, the required equation is the nitrogen oxide gas should be in the reactant side. And also 1/2 mole of oxygen gas. So we need nitrogen oxide and the reactant side. Okay, so we need to reverse it so that we can have nitrogen oxide and the product or in the reactant side. And then why we did not reverse the second equation? It's because we need the nitrogen dioxide gas in the product, so we will not reverse the equation. And remember that if we reverse the equation, the sign will also reverse. So this is positive. So when we reverse it, the sign will become negative. So that's happened here. Okay, it becomes negative because we reversed equation number 1, and equation number 2 stays the same, positive, because we did not reverse. Now we add the equations. So when we add the equation, we cancel out substances that are similar between the two equations, but the cancellation would be on the product and reactant. Product and reactant, or reactant and the product. So let's see. Nitrogen oxide, is it cancelled with nitrogen dioxide? No, because those two substances are different. So let's go to the product. We'll check if it has similar substance with the reactant of the equation number 2. So 1/2 and 2, 1/2 and 2, that means these two are cancelled. And then 1/2 O2, and then we'll have 1 O2. So 1/2 O2 cancelled, but we still have remaining 1/2 O2 here. So we have to write all the remaining substances in the reactant side. Okay, then we have NO, a gas, plus we have a remaining 1/2 mole of O2 gas, and then there's nothing more, so we have to write here the arrow, and then we'll go to the product side. The product side here, we only have NO2. Okay, so this is now the equation that is required. This is the one here. Okay, this is the one. So we got that. And then what we will do now is also again add this heat of formation. So minus 90 plus minus 90.29 kilojoules per mole plus 33.2 kilojoules per mole is equal to 57.1 kilojoules per mole. The sign is carried over by the number with a bigger value. So the number with a bigger value here is 90, and the sign is negative. So that is why the answer will also have a negative sign. So that means this equation, thermochemical equation, is exothermic because the delta H is negative. So if you notice that there is no F here in the symbol, so that means this is what we call the standard enthalpy of reaction, and this is here the standard heat of formation. This one here only is lacking an F. Okay, so the answer here is standard enthalpy of reaction, which is equal to minus 57.1 kilojoules per mole. The general relationship between the heat of reaction and the heats of formation of the reactants and products is described in the following word equation. The standard enthalpy of reaction is equal to the summation of the standard heat of formation of the products minus the summation of the standard heat of formation of the reactants. Okay, so we just have to substitute the given data to the formula. So summation of the products here, 33.2 kilojoules per mole minus that of the reactants, it is 90.29 kilojoules per mole, is equal to 57.1 kilojoules per mole, which is equal. Note that 0 is assigned value for the heats of formation of elements. So here, this is 0 because in the reactant we have oxygen. Okay, that is an element. So note that that 0 is the assigned value for the heats of formation of elements. And again, delta H0 standard enthalpy of reaction and delta H0F standard heat of formation. Let's go to problem number 2. Calculate the heat of hydrogenation of ethane given the following thermochemical equations. So we have 2 moles of graphite or carbon plus 3 moles of hydrogen gas forms 1 mole of ethane. Letter B, 2 moles of graphite plus 2 moles of hydrogen gas forms 1 mole of ethane. And these are the corresponding standard heat of formation. Unknown or the required is the delta H for this form of equation. Okay, and also we need to get this equation at the end because this is the required equation from these 2 equations. So looking at this class, you can see that C2H4 should be in the reactant side. That means this would be what? Reversed. And C2H6 is in the product side, so there is no need for it to be reversed. It will stay as is. So this is positive here and this is negative. Solution. Equation A will remain as it is. Applying Hess Law, reverse equation B and change the sign of delta H. So C2H4 gas forms 2 moles of carbon plus 2 moles of hydrogen gas and it becomes negative. Now we add the 2 equations. So we have the reactant and we'll look at the product side of the other equation if we can cancel similar substances. So 2 graphite cancelled. 3H2 is cancelled with 2H2 here, but so we still have 1 hydrogen remaining here, 1 hydrogen gas. And then the product and the reactant, there is no similar substance, so we have it have to remain as is. Now we will copy the remaining substances in the reactant side. So we have H2, yes, and we have C2H4. If you write H2 first, it is okay, but the correct or the best answer would be C2H4. You write C2H4 first and copy the gas, the state, plus 1 mole of H2 gas will form 1 mole of C2H6 gas. Now we add this up. So because they have similar signs, the symbol will be easy. It is also negative. We add it up. So the answer is 136.8 kilojoules per mole. So the standard enthalpy of reaction of this equation is this. Examining this problem closely, the heat of reaction can be calculated by subtracting the sum of the heats of formation of reactants from the sum of the heats of reaction of the products. Therefore, the equation, the standard enthalpy of reaction is equal to the summation of the standard heat of formation of the products minus the summation of the standard heat of formation of the reactants. Using to calculate the heat of hydrogenation of ethane is equal to minus 84.5 kilojoules per mole minus 52.3 kilojoules per mole, that is for C2H4, plus H2, which is 0 for elements. The answer is equal to negative 136.8 kilojoules per mole. So when subtracting, you need to change the sign here to negative and then proceed to addition. That is why the answer is negative 136.8 kilojoules per mole. Recap of the rules of thermochemistry. Delta H is directly proportional to the amount of reactant or product. If a reaction is divided by 2, so is delta H. If a reaction is multiplied by 6, so is delta H. Delta H changes sign when the reaction is reversed. Delta H has the same value regardless of the number of steps. Now, let's go to everyday application of Hess's Law. Industries. Today, all our mass and low-cost production depends on factories and industries, and all these industries require huge amount of energy. To keep everything the most efficient possible, these industries has to determine the method that is the most effective to produce a product based on the energy needed or released. The most important function of Hess's law may be in industries that choose the burning of fuel, such as in cars for everyday energy. The industries can measure how much energy its fuel releases when it is burned, so that they can make efficient energy choices and save money. The human body. When we talk about the burning of energy, we can also think about the human body. A lot of weight loss application uses this concept to calculate the amount of calories burned during a workout, and a lot of the time they are pretty accurate thanks to the Hess's law. Pharmaceutical industry. For people that lives in cold places, buying the best hand warmer is crucial for survival. The little pack that warms our freezing hands are the best thing to have in winter or when feeling cold. The Hess's law is especially helpful because the manufacturers can use this concept to find out the total change in enthalpy and deduce how many amount of each ingredient is needed to keep you warm for hours. Thank you for watching. If you learned something from this video, please like and subscribe to my YouTube channel. God bless and stay safe, everyone.